Hi, today we are talking about the fifth or the last of the solid principles, Dependency Inversion Principle or DIP for short. We will be exploring the DIP with a simple and a complex example and how it inverts ownership, abstract factory pattern, static and dynamic polymorphism. Please feel free to jump into any chapter of your interest by clicking on the links in the description box. As usual, we will be using derivatives and subclasses to refer to the same idea of subclasses. The dependency inversion principle is basically twofold. First, it says high-level modules should not depend on low-level modules. Both should depend on abstractions. Second, abstractions should not depend on details. Details should depend on abstractions. This is how we can illustrate this principle in a diagram. Instead of high-level policies depending on low-level policies and abstractions depending on details, this principle enforces that they should be the other way around. Before we dive deeper, let's start with a simple example of DIP violation. Here we can see remote control being dependent upon TV. What we actually want is a mechanism to control a device without relying on a concrete implementation like TV. So we can introduce a device interface which the remote control will depend on. Now TV or any other device such as sound system is depending upon device. So we have inverted the dependency, so high-level modules don't depend on low-level modules and they both depend on abstractions, which is first part of the DIP, and details depend on abstractions, which is second part of the DIP. Now let's dive a little deeper into DIP. In the traditional structured software development methods, there was a tendency to create software structures where high-level modules depended upon low-level modules. However, with the introduction of object-oriented programming, this dependency inverted, and let's see how. It is the high-level modules that contain the important policy decisions and business models of an application. These modules contain the identity of the application, yet when these modules depend on the low-level modules, changes to the low-level modules can have direct effects on the high-level modules and can force them to change in turn. It is the high-level policy setting modules that ought to be influencing the low-level detail modules. The modules that contain the high-level business rules should take precedence over and be independent of the modules that contain the implementation details. High-level modules simply should not depend on low-level modules in any way. Moreover, it is high-level policy setting modules that we want to be able to reuse. We are already quite good at reusing low-level modules in the form of subroutine libraries. When high-level modules depend on low-level modules, it becomes very difficult to reuse those high-level modules in different contexts. However, when high-level modules are independent of the low-level modules, then the high-level modules can be reused quite simply. This principle is at the very heart of framework design. So in this more complex example with multiple layers, you can see how we have inverted the relationship between smart home, remote control and TV by introducing device controller and device interfaces. At its core, smart home class orchestrates the system by interacting solely with abstract interfaces rather than concrete implementations. This design creates a clear hierarchy where the high-level components depend on abstractions like device and device controllers, while low-level components like TV and sound system implement these interfaces. This approach ensures that dependencies flow towards abstractions, not concrete implementations, resulting in a loosely coupled system. The architecture makes it easy to add new device types without modifying existing code, as demonstrated by the independent TV and sound system implementations. This design not only promotes code reusability and maintainability, but also makes the system highly testable, as components can be easily mocked and verified in isolation. The overall structure demonstrates how proper application of solid principles, particularly the DIP, leads to a robust and flexible software system. This is how you would implement the same in Java. Now let us discuss some additional concepts. Inversion of ownership. Notice that the inversion here is not just one of dependencies. It is also one of interface ownership. We often think of utility libraries as owning their own interfaces, but when the DIP is applied, we find that the clients tend to own the abstract interfaces and that their servers derive from them. This is sometimes known as the Hollywood principle. Don't call us, we'll call you. The low-level modules provide the implementation for interfaces that are declared within and called by the upper-level modules. Using the inversion of ownership, policy layer is unaffected by any changes to the mechanism layer or the utility layer. Moreover, policy layer can be reused in any context that defines low-level modules that conform to the policy service interface. Thus, by inverting the dependencies, we have created a structure which is simultaneously more flexible, durable, and mobile. Depend on abstractions. This idea indicates that you should not depend on a concrete class, that all relations in a program should terminate on an abstract class or an interface. According to this heuristic, no variable should hold a pointer or reference to a concrete class. No class should derive from a concrete class. No method should override an implemented method of any of its base classes. Certainly, this heuristic is usually violated at least once in every program. Somebody has to create the instances of the concrete classes, and whatever module does that will depend on them. Moreover, this heuristic can be violated with non-volatile classes which do not change much often and that are not used to derive other classes like the string class in Java. However, most concrete classes that we write as part of an application program are volatile. It is those concrete classes that we do not want to depend directly on. Their volatility can be isolated by keeping them behind an abstract interface. This is not a complete solution. There are times when the interface of a volatile class must change, and this change must be propagated to the abstract interface that represents the class. Such changes break through the isolation of the abstract interface. Next, the abstract factory pattern provides an interface for creating families of related or dependent objects without specifying their concrete classes. Let's see how the abstract factory pattern helps comply with the dependency inversion principle in our smart home system. The abstract factory pattern strengthens our adherence to DIP by introducing abstraction layers for both product creation and the products themselves. Instead of the smart home system depending directly on concrete device implementations like TV or sound system or their controllers, it depends on the abstract home device factory interface for creation and the abstract device and device control interfaces for functionality. This creates a dependency structure where both high-level modules like smart home and low-level modules like concrete devices and controllers depend on abstractions. The home device factory interface serves as an abstract layer that decouples the creation logic from the usage logic, while concrete factories like TV factory, sound system factory provide the specific implementations. This arrangement ensures that the high-level smart home module remains completely unaware of the concrete device implementations, allowing us to add new device types without modifying existing code. The dependency flow is inverted from smart home to concrete device and controllers to from smart home to abstractions and concrete implementations to abstractions. This structure fully satisfies both parts of the DIP principle. High-level modules do not depend on low-level modules and abstractions don't depend on details. This is how the class diagram of the compliant solution would change if we use the abstract factory pattern. I have marked changes in green. This is how you would implement the same in Java, and I believe you can go over the code to understand the implementation. The last concept we are going to discuss is dynamic versus static polymorphism. What we have already discussed with device interface is dynamic polymorphism, which is implemented with method overriding and where the actual method is determined at runtime. We define static polymorphism through method overloading, where the actual method is determined at compile time and implemented in the remote control class as shown here. Finally, as with every solid principle, striking the balance is a key, as you don't want to bombard your architecture with so many interfaces and factories. If you found this content useful, please like, share and subscribe for similar content. Hope to see you in another video. Until then, happy coding!